History of Math, Lecture 14 out of 28. So this is exactly halfway through the course. And we're up to chapter 6, which is on the 17th century Italian mathematician Cardano and the solution of the cubic. It's hard to give a precise date for this. So the book gives 1545, which is an approximation, which is exactly in the middle of the 16th century. So let me just review. Suppose we have a linear equation. The linear equation looks like ax plus b equals 0, and the leading coefficient a is not 0. Or you could have a quadratic equation. It looks like ax squared plus bx plus c equals 0. And again, the leading coefficient is not 0. You could have a cubic equation. Ax cubed plus bx squared plus cx plus d equals 0. And again, the leading coefficient, the a, is non-zero. You could have a polynomial equation of degree 4. That's called a quartic. Ax to the 4th plus bx cubed plus cx squared plus dx plus e equals 0. And again, to say it's of degree 4 means that the leading coefficient is not 0. Or you could have a 5th degree equation, which is called a quintic. So then the leading term has degree 5, ax to the 5th plus bx to the 4th plus cx cubed plus dx squared plus ex plus f equals 0. And again, to say it's quintic means that the leading coefficient is non-zero, and so forth. So for every positive integer n, you have polynomial equations of degree n. And how do we solve them? Or generally, the problem is if you have an equation, find the solutions. So the solutions are numbers x that you plug in and give you 0. So for the linear equation, that's easy. You put the b on the other side of the equation and divide by x, and divide by a, you get the solution x is equal to minus b over a, which is okay because you know a is not 0, so you can divide by it. For the quadratic equation, you get the solution. This is what you're supposed to learn in high school, or certainly in pre-calculus, minus b plus or minus the square root of b squared minus 4ac over 2a. Again, you're dividing by a, which is non-zero, so that's okay. The only issue here is that what's under the square root sign might be negative, in which case there's no real solution. But if there is a real solution, this is what it is. It's one of these two numbers or both of those two numbers. All right. So both of these were known, certainly in ancient times. They were known to the Babylonians long ago. That was known in India. In Indian mathematics, you find this. It's hard to know where else such a thing might be known because it all depends on whether the documents, the books, the papers, whatever you might call them, which contained ancient writings, survived for 1,000 or 2,000 years. And depending on where one happened to live and what one might write on, certain materials last for thousands of years, and certain materials decay over time or they're not available. So, for example, a lot of ancient Chinese mathematics disappeared because the material that it was written on simply decayed over time. Whereas the Babylonians used clay tablets. They wrote in soft clay, and they put it in a fire and burned it, and it became like a rock. So Babylonian mathematical scraps, segments, documents, just like other Babylonian documents from 2,500 or 3,000 years ago, they survived because the tablets they were written on were basically turned into stone, and the stone lasts forever. In any case, in ancient times, over 2,000 years ago, it was certainly known in parts of the world how to solve a first-degree linear equation and how to solve a second-degree quadratic equation. But a third-degree equation, that was a mystery. And it wasn't until the 16th century that there was an explosion in knowledge in Italy, and the Italian mathematicians were able to solve a cubic equation. And this is really extremely important. So I'm going to go through it again. I went through it one way last week, but I'm going to go through it again from the beginning today. One of the interesting things is that there still was a geometrical nature to the solutions, even in 16th century Italy, because modern algebraic notation was in its infancy. So how do you start? So suppose we have the equation ax cubed plus bx squared plus cx plus d equals 0. So step one is to change variables so the x squared term disappears, vanishes. And how can one do that? Well, one can always make the following substitution. One can decide whether one wants to first divide by a and then make the substitution, or make the substitution and then divide by a. Suppose we let x equal y minus, let's see, what would be a good thing to divide by?
I'm sorry, I can't see. Can you move the paper down, please? Thank you.
Okay. So if you make this y minus, I want to make this something over 3b, and sorry, y minus b over 3a. Right, so a is different from 0, so this makes sense. Now, if you make this substitution, and substitute. So when you substitute, what do you get? You get ax cubed, that's a, y minus b over 3a cubed, plus bx squared, which is y minus b over 3a squared, plus cx, which is c times y minus b over 3a, plus d equals 0. So when you make this substitution, you get this equation. Now, what you have to know is if you take, let's say, y minus some number p, and raise it to any power. Suppose you raise it to the nth power. What do you get when you expand this? So this is y to the n minus np y to the n minus 1 and lower order terms. So this you must know. If you don't know it, memorize it immediately. Like, for example, y minus p squared is y squared minus 2py plus something, right? Just square this. You get a y squared, and then the coefficient of y is minus 2p. If you have y minus p and you cube it, you get y cubed minus 3py squared plus lower order terms. When you take y minus p to the n, that's always y to the n, and the coefficient of the next term, y to the n minus 1, is n times p. So this you must know. Well, of course, I just showed it to you, so now you know it. But this you have to know. So in particular, y minus p cubed looks like this. So when you expand this, what do you get? You get a y cubed. My p in this case, this number, is b over 3a. Y cubed minus 3 b over 3a y squared plus lower order terms. Lower order terms means lower powers of y. What do I get when I expand this? I get b times y squared minus 2b over 3ay plus the constant term. And I get the rest of this. But this involves y and constants. This doesn't involve any power of y higher than the first. Right? So this is just high school algebra. Now, high school algebra is not a pejorative. High school algebra can be hard. But this you have to understand. So if there's a question about this, just ask me right now.
What, going back to let x equals, why did you choose it to be y minus b over 3a? Is it just because it's cubed, you put the 3 in front of the a?
I do it because it's going to work. Because if you look at this, when I cross multiply, let's say this is a y cubed, the 3's cancel, minus b over a y squared plus other stuff. Here I have by squared and other stuff, but this other stuff only involves constants or y. There's no more y squared. And when I multiply, what do I get here? I get a y cubed. Here the a's cancel, minus by squared plus by squared plus other stuff. And if you look at this, you see minus y squared plus y squared cancel. So I end up with an equation where there's no y squared. It's ay cubed plus something, call it cy plus d equals 0. There's no more y squared. So I choose this substitution because it's going to eliminate the y squared term or the quadratic term. And I know that because I remember this formula from high school algebra, and I choose my number p to be b over 3a because it works. Now, another way to get it is as follows. Suppose I had, let me write down this equation again, ax cubed plus bx squared plus cx plus d equals 0. Suppose I want to make substitution. So suppose I'm going to let x equal y minus p, and I want to choose p to kill the quadratic term. Okay. So if I let x equal y minus p and I substitute it in, I get a y minus p cubed plus b y minus p squared plus c y minus p plus d equals 0. When I expand this, I get a y cubed minus 3py squared plus other terms plus b times y squared minus other terms plus c y minus p plus d equals 0. I only care about the terms that involve a square. See, when I expand this across, I get ay cubed minus 3apy squared. Here I have plus other stuff, plus by squared plus other stuff. If I put these two together, this is ay cubed. And then what is the coefficient of y squared? I have minus 3AP plus B, or B minus 3AP. Right? So if I just substitute y minus p, the coefficient of y squared is this. And I want this to be 0. So b minus 3AP equals 0 if p is equal to b over 3a. So I could also work backwards and see this is what I have to choose p to be. I have no other choice. So when I make this substitution, if I let y equal x minus b over 3a, we get an equation ay cubed. There's no more quadratic term, just something times y plus a constant equals 0. And a is always non-zero. A was the leading coefficient. And I can divide by a just to make this equation look simpler. You get y cubed plus c over ay plus d over a equals 0. And what the Italians did, for whatever reason, is they put this term on the other side of the equation. So the cubic is of the form y cubed plus something that's called m times y equals n. So the equation gets reduced, the cubic equation is reduced to something which looks like this, which is called a depressed cubic, which simply means no quadratic term. So given any cubic equation, remember we started with the equation ax cubed plus bx squared plus cx plus d equals 0 with a non-zero. That's the general cubic. But by making a substitution and dividing by a, we can always put it into this form. And if where y is equal to x minus b over 3a. So if you can solve this equation for y, then you know x, because if y is x minus b over 3a, then x is y plus b over 3a. So if you can solve this for y, then you can get x, which is the solution of the original equation. So the first step in this approach to solving the cubic is to take your cubic and immediately transform it into the depressed cubic. Let me just do an example. I'll just pick numbers at random. Suppose I have 3x cubed plus 4x squared minus 5x plus 7 equals 0. Right. So A is 3, B is 4, C is minus 5, D is 7. So I want to let y be x minus b over 3a, which is x minus 4 over 3 times 3, which is 9. So I'm going to substitute y is equal to x minus 4 over 9. So is there any question about how I got this? This is the cubic. These are the values of a, b, c, and d. You let y equal x minus b over 3a. B over 3a is 4/9. So I get 3 times x minus 4/9 cubed plus 4 times x minus 4/9 squared minus 5 times x minus 4/9 plus 7 equals 0. Let me expand this. What is this? This is x cubed minus 3 times 4/9 x squared plus 3 times 4/9 squared x minus 4/9 cubed, right? You have to know how to expand. You know, x minus p cubed is x cubed minus 3px squared plus 3p squared x minus p cubed, right? Just as you know that x minus p squared is x squared minus 2px plus p squared. Right? Again, if you don't know these, memorize them. Just like you had to memorize the times table, 3 times 7 is 21, you have to memorize these expansions of a binary, quadratic, and cubic, right? You have to know this. So this is x minus 4/9 cubed plus 4 times x minus 4/9 squared, that's x squared, minus 2 times 4/9 x plus 4/9 squared minus 5 times x minus 4/9 plus 7 equals 0. So if I multiply through by 3, what do I get? I get 3x cubed minus, here I have 12 over 9. Actually, if I multiply by 3, I get 9 times 4 over 9, so the 9's cancel, minus 4x squared, plus 9 times 4 over 9 squared, so that's 16 over 9x, minus 4 cubed, 4/9 cubed, 4 cubed is 64, 9 cubed is 729, I think. Plus, let me cross multiply this, 4x squared minus 4 times 2 times 4, that's 32 over 9x, plus 16 over 81 times 4, 64 over 81, minus 5x, plus 20 over 9, plus 7 equals 0. But all we care about, I mean, the whole point is to get rid of the square term. Actually, I'm sorry. I should have, I'm letting, this should be a y. Sorry. Let x equal y minus b over 3a. So these are just y's here. We're substituting and changing the x to a y. But again, all that's important for us is the y squared. You have minus 4y squared plus 4y squared. They're gone. They cancel. So our equation becomes 3y cubed plus something times y, 16 over 9, that's a y, minus 32 over 9, minus 5, plus a constant term, minus 64 over 729, plus 64 over 81, plus 20 over 9, plus 7 equals 0. So now I have a cubic, but there's no square term. It's y cubed and y and a constant. And then I just divide by 3. I get y cubed plus a third of this and a third of this. So this is, and then I bring this to the other side. So this is y cubed plus some number m times y equals n. Okay. So this is how your substitution eliminates the quadratic term. So this is the depressed cubic that comes from this equation. Right. Again, there's a lot of high school algebra, and you got to do it. So let me change the y back to an x again, because we're more used to x as a variable. So we reduced the problem to solving the depressed cubic x cubed plus mx equal n. Now, as the text described, Cardano still somehow thought of things geometrically. And I should emphasize this. In the 16th century, most people, almost everyone, including most mathematicians, did not understand negative numbers. So when they write a cubic, the numbers m and n are positive. What would happen if n were negative? Then they would bring it back to this side, so minus m would be positive. If m were negative, they would bring it to the other side, so minus m would be positive. So that's one reason why the equation is written like this. And Cardano considered this one of several cases. He would also consider separately x cubed plus n equals mx, and x cubed equals mx plus n, and x cubed plus mx plus n equals 0, because they only consider cases where m and n were 0 or positive numbers. If m or n is 0, there's nothing to solve, because if m is 0, this is just the cube root of n, and if n is 0, this is x equals 0 or quadratic. So this is the cubic. So let me describe how Cardano decomposes a geometric cube. What do we mean by geometric cube? Not a cubic equation, but a cube like you draw in geometry. So this is a cube. Okay? A geometric cube. And suppose the side, each side has length t. But now Cardano thinks of this as follows. He takes this side of length t and he breaks it up into two pieces. A piece u, and then the other piece has to be t minus u, because they have to add up to t. And he does that here too. Well, this is u, and this is t minus u. And this is u, and this is t minus u. And in the low, so it's hard. You have to somehow teach yourself to think geometrically. In this lower right-hand corner of the cube, you can put a little cube whose side is a square of base t. So down here in the corner of the cube, I have a little cube whose side is t. And if I look at this corner of the cube, or let's say this side corner of the cube, in this face, this is a rectangle. This is t minus u. This is u. This is t minus u. And if I extend this up to the top, this is u, this is t minus u, this is t minus u, and this is t minus u. So on this face of the cube, I have a square in the lower right-hand corner whose side is u, I have a square in the upper left-hand corner whose side is t minus u. And then I have these two rectangles, u by t minus u. And let me actually do this across. So this is t minus u, and this is u. And let me decompose this into u and t minus u. Okay. So this is u and t minus u. Now, now's the part where you have to look at this very carefully. So in the lower right-hand corner, I have a little cube whose sides are u. So this point is right here above this. It hits this. So this is u. This is on the top of the cube. This is u in from both sides. So this is t minus u, and this is t minus u. So on the top of the cube, this is a square of size t minus u. This is a square of size u, and these are rectangles. And I draw the cube inside the big cube, where one corner is here, and the sides are t minus u. So if you look at the book, you'll see a better drawn picture of this, but so let me see. So down here, I have a cube of side u, and up here, I have a cube of side t minus u. So in this big cube, I have a little cube at the lower right-hand corner and another cube at the upper left-hand corner. Plus, I have the stuff that's left over. So what is left over? So here I have, this is a kind of a rectangular solid, a slab, whose sides are t minus u, the height is t, and the thickness is u. So this is t by t minus u times u. That's the volume of that slab. And over here, I have another slab with the same volume. And above this little cube, I have sitting on top of this little cube is another slab, this green slab. The base is u squared, and the height is t minus u. And below this cube, I have a slab whose base is t minus u cubed, t minus u squared, and whose height is u. So you can really, you should look at the book. This is on page 143. You have the cube. The volume of the cube is t cubed, right? It's a cube whose side is t. But I've divided it up into 6 pieces. I have a small cube at the bottom whose volume is u cubed. I have another cube at the top whose side is t minus u, so the volume is t minus u cubed. I have 2 slabs that look like this. Each of them have volume ut times t minus u, or tu times t minus u, but there are two of them, 2tu times t minus u, plus I have the piece sitting on top of this little cubed, which is u squared times t minus u, and the piece under this cube, which is t minus u squared times u. So I have this formula for the volume of a cube. So let me just write this down again. So if I take any number u between 0 and t cubed is u cubed plus t minus u cubed plus 2tu t minus u plus u squared t minus u plus t minus u squared times u. Now, I worked out this formula geometrically by taking the cube and cutting it up into 6 pieces. If you prefer algebra, of course, nowadays, you can just check this identity algebraically. Just expand the right-hand side. You'll get everything canceling except a t cubed at the end. So let me write this slightly differently. So I have t cubed minus u cubed actually, just to make it easier for you, I'll follow the form in the text. So, well, I can do that. T cubed minus u cubed equals everything on this side. T minus u cubed plus 2tu t minus u plus u squared t minus u plus t minus u squared times u. And you notice there's a t minus u in each of these terms, so I can factor out t minus u, and I get t minus u squared plus 2tu plus u squared plus t minus u times u. I mean, that's correct, but actually, let me let me leave this term. This is completely correct, but I'm just writing this down again. T minus u cubed equals t minus u cubed plus, and from these 3 terms, I'll factor out the t minus u. So I get 2tu plus u squared plus t minus u times u, which is t minus u cubed plus t minus u. Let's see, when I expand this, what do I get? I get, well, let me just do it. 2tu plus u squared plus tu minus u squared. The u squared cancel. You get t minus u cubed. Tu plus tu is 3tu plus 3tu t minus u. So just rearranging this expression for the partition of the cube, we get t minus u cubed plus 3tu times t minus u equals t cubed minus u cubed. And you might say, well, what good is this? Well, remember, we're trying to solve the depressed cubic. The depressed cubic is x cubed plus mx equals n. So suppose we can choose t and u such that 3tu equals m and t cubed minus u cubed equals n. Then x equal t minus u solves the cubic. Right? So from our original expression for this partition of the cube of psi t into two small cubes plus four parallelepiped, four rectangular slabs, we have this equation, which we can rewrite like this and just rearrange so it looks like this. So we get this identity. And this is true for all numbers t and u. T minus u cubed plus 3tu times t minus u equals this. Now, if we can find numbers t and u such that 3tu is equal to m and t cubed minus u cubed is equal to n, and we set x equal to t minus u, we've solved the cubic. So this explains the construction that we went through last Wednesday, but I'm going to do it again right now. So what we've just shown is the following. We have the depressed cubic. Depressed means no quadratic term. Doesn't mean unhappy. X cubed plus mx equal n. Right? Find numbers t and u such that 3tu equals m and t cubed minus u cubed equals n. If we can solve these two equations, then x equal t minus u is a solution of the cubic. Right? And then the question is, so we're given positive numbers m and n, or any numbers for us, but for the Italians, it was positive numbers m and n. Find positive numbers t and u that solve this equation. Right? So what can we say? Well, first of all, if 3tu equals m, if we can find such t and u, then necessarily u, solve this equation for u must equal m over 3t. So then t cubed minus u cubed is t cubed minus m over 3t cubed, which is t cubed minus m cubed over 27 t cubed, and t cubed minus u cubed has to equal n. So if we can solve this for t, then from t we get u and we're done. Now this is a strange equation because the variable is in the denominator, but t is going to be positive, so let's just multiply by t cubed, you get 2 to the 6th minus m cubed over 27 equals nt cubed. Or if I bring this to the other side, I have t to the 6th minus nt cubed minus m cubed over 27 equals 0. Solve this for t. And you might say, well, now that's ridiculous because we started with the cubic that we were trying to solve, and suddenly we have a polynomial of degree 6 that we want to solve. But we're lucky because we have t to the 6th power, but the only other power of t is t cubed. And it's good to remember that 6 is 3 times 2. So this is the same as t to the 3 times 2 minus nt cubed minus m cubed over 27 equals 0. And t to the 6th is t cubed squared. So if I write t to the 6th as t cubed squared, what I now have is, this is a quadratic equation in t cubed. And I know how to solve a quadratic equation. So t cubed is minus b is minus n, so that becomes plus n, plus or minus the square root of b squared, minus n squared is n squared, minus 4 ac, a is 1, and c is m cubed over 27, so minus times minus is plus 4 m cubed over 27 divided by 2a, which is divided by 2. Which, if I like, I can rewrite as, let's see, this is n over 2 plus or minus 1/2 the square root of, if I factor a 4 out of this is 4 times n squared over 4 plus m cubed over 27, plus 4 times n squared over 4 is just n squared. Of course, the square root of 4 is 2, so I could take this out and it cancels this 1/2. So what I get is t cubed is n over 2 plus or minus the square root of n squared over 4 plus m cubed over 27. And I want t to be positive. If this n squared over 4 plus this is bigger than n over 2. So if I take the minus sign, this will be negative. So I take the plus sign. So this will be positive. So t cubed is equal to, we're going to choose the plus sign, n over 2 plus the square root of n squared over 4 plus m cubed over 27. So t is the cube root of that. So this is a little messy expression, but it's certainly correct. T is the cube root of n over 2 plus the square root of n squared over 4 plus m cubed over 27. And that's what t is. And what is u? U, we know that, let's see, t cubed minus u cubed equals n. So u cubed is t cubed minus n. This is t cubed. T cubed is n over 2 plus the square root of n squared over 4 plus m cubed over 27 minus n. N over 2 minus n is minus n over 2. So u cubed is minus n over 2 plus this square root. So u is the cube root of this mess. It's the cube root of minus n over 2 plus the square root of n squared over 4 plus m cubed over 27. So this is u, and this is t, and x equals t minus u. So this is cube root of n over 2 plus square root of n squared over 4 plus m cubed over 27 minus cube root of minus n over 2 plus the square root of n squared over 4 plus m cubed over 27. And the magic is done. So if you have the depressed cubic, x cubed plus mx equal n, that's the solution. Now, it may be a little bit complicated, but of course, it took almost 2,000 years to get from the quadratic equation solution to the cubic equation solution. And the reason it took 2,000 years was because it was complicated. So this is Cardano's formula. And this truly is one of the great achievements in the history of mathematics, especially from the point of view of in the Middle Ages, there was very little scientific progress in Europe. All the scientific progress took place either in India and China or in the Arab world, in the Muslim world, which was the repository of sort of knowledge of the time. And the Renaissance really meant, people think of the Renaissance as rebirth, the rebirth of civilization or progress, intellectual progress in Europe, which came about because the manuscripts from the Arabic language somehow filtered into Europe, were translated into Latin, which was the only thing people in Europe could read. And from that knowledge, they then started to move forward. All right. Let's look at an example. So the example that the text like is x cubed plus 6x equal 20. So m is equal to 6 and n is equal to 20. So what is the solution? Solution is x equal to the cube root of n over 2. Let's see. N squared over 4 is 20 squared over 4 is 400 over 4 is 100. M cubed over 27 is 6 cubed over 27. 6 cubed is 3 cubed times 2 cubed. This is 8 times 27 over 27, or 8. So what's in the square root sign is 100 plus 8 minus the cube root of minus 10 plus the square root of 108. So this is a positive number, and this is the solution of the equation. Now you might say the following. Let's see, there's something a little bit puzzling about this. So remember, when we looked at the equation x squared plus 6x equal 20, one solution is x equal 2, because x equal 2. Right? 2 squared plus 6 times 2 is 8 plus 12 is 20. So one solution is x equal 2. Now, a cubic equation you expect might have 3 solutions. If I take x cubed plus 6x, this is the same as x cubed plus 6x minus 20 equals 0. If I divide this by x minus 2, so you're supposed to know how to divide one polynomial by another. This goes in x squared. I get x cubed minus 2x squared. Subtract, I get 2x squared plus 6. X minus 2 goes into this 2x times. This is 2x squared. Let's see. 2x squared minus 4x. And when I subtract, I get 4x plus 6 minus 20 is 4x minus 14. Is that right? So I'm just, let me just explain what I'm doing. If you have x cubed plus 6x equal 20, that's the same as x cubed plus 6x minus 20 equals 0. And one solution is x equal 2. So if I take this polynomial, let me divide it by x minus 2. X minus 2 into x cubed plus 6x minus 20. X into x cubed goes x squared times. So I get x squared, so I get x cubed minus 2x squared. So when I subtract, I get 2x squared plus 6x minus 20. X into 2x squared goes 2x times. 2x times this is 2x squared minus 4x minus 20. When I subtract, I get 10x, minus 4. 2x squared minus 2x squared minus 4x. And when I subtract, I get 10x minus 20. And x into 10x goes 10 times. 10x minus 20, it goes in evenly. So x cubed minus 6x minus 20 is equal to x minus 2 times this quadratic x squared plus 2x plus 10. So if you want to solve this equation, the solutions of this equation, so I'm using a little bit more algebra. I'm moving up to the 18th century maybe. One solution is x equal 2. If you have a solution different from 2, then x squared minus x squared plus 2x plus 10 has to equal 0. But this is a quadratic. We know the solutions of this from the quadratic formula. Minus 2 plus or minus the square root of b squared minus 4ac over 2, which is minus 2 plus or minus square root of minus 36 over 2, which is square root of 36 is 6. I get minus 1 plus or minus 6 over 2, 3 root minus 1. This is imaginary. This is a complex number. It's not real. So this kind of, again, algebra tells us that for our cubics, x cubed plus 6x equal 20, which is the same as x cubed minus 6x minus 20 equals 0, there's one real root, x equal 2, and the other two are complex numbers. So now we have a little bit of a puzzle. So when we have x cubed plus 6x equal 20, one solution that's positive and real is x equal to, what was it? Cube root of 10 plus the square root of 108 minus the cube root of minus 10 plus the square root of 108. And this is a positive number. So this is one positive root of the solution, but we also have the solution x equal 2. So x equal 2 is a positive number that solves this equation. And this messy looking thing is another positive number that solves this equation. But there's only one positive solution, right? That was the argument we just gave. So we must have that the cube root of 10 plus the square root of 108 minus the cube root of minus 10 plus the square root of 108, that's just equal to 2. It's just a funny way of writing 2. So as a fun exercise, prove this. You might try and figure out, how can you prove this equals this? You might say, prove this exactly and check numerically. That means with a calculator or a computer. Okay. But what you have to try to remember is Cardano's solution of the depressed cubic. You have x cubed plus mx equals n. The solution is x equal to the cube root of n over 2 plus that quadratic. Minus the cube root of minus n over 2 plus the quadratic. Okay. Now, there's a very interesting point that comes up, because you know from quadratic equations that some quadratic equations do not have real solutions. So we saw a moment ago that the quadratic x squared plus 2x plus 10 has no real number solutions, no real solutions. That doesn't mean it doesn't have solutions. It means the solutions are in the complex numbers. They're not real numbers. Suppose we consider the cubic x cubed minus 15x equals 4. So by trial and error, we can see that x equal 4 is a solution. If you let x equal 4, 4 cubed minus 15 times 4 is 64 minus 60 is 4. So this equation has a solution, x equal 4. what does Cardano's formula give us? So m is minus 15, n is 4. So we have the solution x is the cube root of n over 2 n is 4, so n over 2 is 2, and n squared over 4 plus m cubed over 27 is, let's see, n squared, that's 16 over 4. M cubed, what is 15 cubed? So 15 is 3 times 5. So let me write this as 15 is 3 times minus 5 all cubed over 27, which is 3 cubed. So these cancel. 16 over 4 is 4. Minus 5 cubed is minus 125 is minus 121. So we get x cubed. So x is equal to n over 2 plus the square root of n squared over 4 plus m cubed over 27 minus 21 minus, sorry, this is 4. This is 4 over 2. This is 2 minus the cube root of minus 2 plus the square root of 121. Minus 121. And now we have a problem because these square roots are not real numbers. They're complex numbers. But we cannot say that it follows that the equation has no real solutions, because we know the equation has a real solution, that x equals 4 is a solution. So somehow this complex number minus this complex number equals 4. Or another, what that really means, there has to be a way to understand the square root of a negative number. So this was a problem in the 16th century. And it took another more than 100 years to figure out what complex numbers meant and were. But you see almost immediately, working with quadratic and cubic equations, that there has to be a way to deal with complex numbers. There has to be a way invented to understand what these things are. And we're not going to talk about that now. Hopefully you've already seen this in some course in algebra or calculus, Calc 3 certainly. But starting with this cubic equation, which we know by simple trial and error does have a positive real solution, that number has to be the number given by Cardano's formula. But from Cardano's formula, we have square roots of negative numbers, and there has to be a way to deal with them. Actually, I'm curious. X cubed minus 15x equals 4. That's the same as the equation x cubed minus 15x minus 4 equals 0. We divide that by x minus 4. Let's see what we get. This will give us the other two solutions for the cubit. So x minus 4 divided into x cubed minus 15x minus 4. And if you don't know how to divide one polynomial by another, that's just long division. So it's worth figuring that out. So x squared, x into x cubed goes x squared times. This is x squared minus 4x squared. When you bring this down, you get 4x squared minus 15x minus 4. X goes into this, 4x times 4x squared minus 16x minus 4. Bring this down, you get x (4x squared minus 16), you get x minus 4. This goes in once. x minus 4. So x cubed minus 15x minus 4 equals x minus 4 times x squared plus 4x plus 1. And if we wanted to solve the equation x squared plus 4x plus 1 equals 0, x is minus b plus or minus the square root of b squared minus 4ac over 2. That's minus 4 plus or minus the square root of 12 over 2. Square root of 12 is 2 root 3. So this is minus 2 plus or minus the square root of 3. So in fact, this quadratic, this cubic, x cubed minus 15x minus equals 4, has 3 solutions and they're all real. One of them is x equal 4, and x equal minus 2 plus root 3, and x equal minus 2 minus root 3. So it has to be that this expression, which involves some complex numbers, there's cancellation of the imaginary parts, and the result is one of these 3 numbers. This is positive, these 2 are negative, so it has to be this guy. Let me add one last remark, and this is discussed in much more depth, if you like, in the further topics at the end of this chapter. So we can now solve cubic equations. What about quartic equations? Even in the depressed form, which would be like x to the 4th plus mx squared plus nx equal p, let's say. There is a solution. So shortly after Cardano solved the cubic, one of his students and colleagues figured out how to start with a quartic equation and reduce to a cubic. And once you reduce it to a cubic, you can solve. So the Italians in the 16th century also learned how to solve quartic equations. So then there come to quintic equations. Ax to the 5th plus bx to the 4th, cx cubed, dx squared, ex plus f equals 0. A non-zero. No solution could be found. By a solution, we mean a solution that just involves the coefficients of the equation and taking roots, like maybe you need square roots, cube roots, maybe you need 4th roots, 5th roots, some roots. But no one could find a formula for a solution. And in the 19th century, it was proved impossible. So it's not that no one was ever smart enough to figure out how to solve the general 5th degree polynomial. Turns out it's impossible to do. And for this, you have to know a little bit of abstract algebra. If you take 314, that first semester of algebra, that gets you partway there, but you need at least the second semester of algebra, abstract algebra, to learn how to learn the impossibility of this equation. And it was due to 2 mathematicians. One was a Norwegian named Sophus Lie, pronounced Lee, and the other was a French mathematician named Évariste Galois. And they both did this when they were in their 20s, and they were both dead before they were 30. Sophus Lee died of malnutrition. He couldn't get a decent job, and it's cold and chilly in Norway. And Sophus Lee died when he was about 28 or 29. Évariste Galois was even younger when he died. He died in a duel. Someone called his girlfriend a prostitute, and he got angry. She was a prostitute. He just got angry. So, as the French like to do in the 19th century, he challenged this guy to a duel with pistols, and he got shot and died. So that's part of the reason why there used to be a belief in mathematics that you only could do great work when you were young, because these two guys both did great work and they died in their 20s, but doesn't seem to be necessarily the general case. But something to look forward to is in sort of algebra 2. By that I mean not high school algebra 2, but second semester of algebra. You learn what is called Galois theory, which, among other things, it's a very powerful technique. And among other things, it proves that there is no general formula to solve the 5th degree polynomial. So for any of you who might be math majors, if there's a chance to take second semester algebra, I would encourage it. Okay. Anything else for today? I'm done. I mean, that's exactly the end of chapter 5. And we move ahead next on Wednesday, 100 years to the 17th, beginning of the 18th century. And we cross the channel from France and Italy to England and learn something about Isaac Newton, who was in a class by himself. Newton and Archimedes certainly were in class by themselves in the history of mathematics. Right? Okay.